Priya, you can start, please.
Yes, ma'am.
Hello, am I
Hello,
audible,
hello.
sir?
Yes, yes, absolutely.
Good morning, sir. Good morning to all the respected guests of honors, authorities, and faculties present here. I welcome you all on second day of 1 week online faculty development program sponsored by AICT IST on recent developments in AI and robotics. I, Engineer Priya Mittal, Assistant Professor, Department of Civil Engineering, BFCT, feels immense pleasure to host this session today with you all. Now, I would like to welcome our today's first speaker, Dr. Sukhjeet Singh Dhami, presently working as professor and head in Mechanical Engineering Department, NITTTR, Chandigarh. He completed his BTech, MTech, and PhD from Punjab Engineering College, PEC, Chandigarh. His research interests are mechatronics, automation, modeling and simulation, computer machine interfacing, and condition monitoring. He is having more than 25 years of teaching experience. He published more than 65 research papers in international and national research journals and conferences. Dr. S.S. Dhami guided more than 7 PhD and more than 60 MTech theses, and 20 are under progress. On behalf of Baba Farid College of Engineering and Technology, we welcome you, sir, to speak over today's topic, sensors and actuators in robotics. Thank you so much, sir, for your kind presence.
Thank you, madam. Thank you so much for a nice introduction. So, if all the participants are there, may I start with the program?
Yes.
Okay, fine. So, madam, is my screen visible?
Yes, sir, your screen is visible.
Okay, thank you so much. Okay, good morning, friends. Welcome you to the first session on the second day of the AICE ISTE FDP on recent developments in AI and robotics, being conducted by Baba Farid College of Engineering and Technology, Bathinda. I'm happy that they have floated this good program. The contents that are covered in this program are very good, and leaving me aside, they have invited very good speakers. So today our topic is sensors and actuators in robotics. So we will begin our discussion with a video that is recorded in our laboratory, and then accordingly we will discuss the sensors and actuators that are required in robotics. So this is a laboratory robot Scorbot ER4U available in our laboratory. So this is the robotic manipulator, and this is the teach pendant, the controller, and on the PC screen you see the shot of the RoboCell software that is used to control or program this robot. Let us first see the video, then we'll again come back to this slide and proceed. So what we are going to see is a pick and place program in action. the robot will be picking an object from one place and putting it at another place, and it will be repeating this action. Okay, so what you saw here is that there is an object which is placed here at a predetermined location. The robot was initially at its what is called as home position. It moved its wrist to the desired location and then opened the gripper, then picked up the object and took it to the new location. So it was repeating these actions. Now, what all is required in this in repeating these actions is that first of all, the movement is required, and then the force to grip the object is required. So we need actuators for carrying out any providing any force or providing motion in a operation. Second thing is that the motions have to be controlled. So we have to see that the robot is following a certain path, or maybe it is able to reach certain points in the space. And that means what we want to have is controlled motion. So to have a controlled motion, we will need to measure the motion. So the sensors and actuators, they form the basic parts of a robot apart from the controller. Now, let us have a look at the robot once again. So what you see here is that in the manipulator, there are some motors installed here, and there are some sensors also that we will see as we progress. Then how do we make the robot carry out a certain operation? So you just saw the robot moving to predetermined locations in space. So what we do is using the teach pendant, we move the individual joints of the robot and make the robot wrist reach at a location in the space which a human operator is watching visually. Right? So once that point is reached in the space, that position will be recorded, and that position is recorded typically in terms of the joint angles. Then in the same fashion, we make the robot reach the different positions in space as are required as per the operation, and we record all the positions, and then we make a program and make use of those recorded positions in that program. Then we run the program and the robot keeps on performing the same operation. Now, in making the robot move manually to the desired locations for recording them, we make use of teach pendant. So basically the teach pendant has a number of buttons on it to make the individual joints move, or maybe to make the robot move in a X, Y, or Z coordinate direction. So I'm sure all these things you had in your previous sessions yesterday. There was a session on introductory part was there, and I think kinematics was there. So making use of this, and then we record the positions, and then we make the program in the computer, or maybe in some cases in the industrial robots, the teach pendants, those are quite big in size, so we can make the program on them only. Here in this case, this teach pendant is a small one, we cannot make a program here exactly. Now all the motors on the robot, all the sensors on the robot, they are attached to this controller. Similarly, the teach pendant is attached to this controller, and the PC is also attached to this controller. And so we have a complete system. Now let us discuss first of all the actuators. So in large robot, we will typically have AC motors. In smaller robots, we will have DC motors. Or in robots which require, say, very heavy operation, we will have hydraulic motors or hydraulic cylinders. So these are some of the typical actuators that are required in motors. Classical DC motor. Classical DC motor means a simple motor, and then geared DC motor, right? That which has a gear attached to the motor for manipulating the torque and speed. Then pneumatic and hydraulic actuators, so they can provide linear motion or they can also provide rotary motion. Then industrial servos. Servos means that where there's a feedback from the rotation of the motor. And then stepper motors, which move in steps. So let us have a look on this robot's actuators. Now, a number of motors are required to operate the robot manipulator. Why number of motors? Because the robot has multiple joints, and for each joint, typically we will have one motor. So for example, this robot, this is the shoulder joint of the robot, and the shoulder joint has 2 degrees of freedom. It can rotate in 2 directions. Like if we slightly go back to this video and see it once again, I'll discuss the 2 motions. You see it is moving from left to right, and it is moving down also. So one motion is which this arm is moving here in the downward direction, and then it is also moving from left to right. That is the second degree of freedom. So now only this joint was moving. Now this joint as well as this joint is moving, and this joint, the shoulder joint, was moving in 2 degrees. Right? It was rotating about this also, it was rotating in the horizontal plane also. So we have 2 degrees of freedom here for the shoulder joint, then 1 degree of freedom for the elbow joint, and then there is this is the wrist. So this is a tool, which is a gripper in this case, attached to the wrist. So we will need 1 motor for 1 degree of freedom. So 2 motors are required for the shoulder joint, 1 motor for the elbow joint, and then for the wrist we will require motors. Now if you look at this close-up of this portion, you will see 1, 2, 3, there's another motor at the back, 4, right? And there's another motor which is inside this base, which is not visible to us. So that motor makes the robot move in this joint moves in the horizontal plane. Now all these motors, they are servo motors, and they have their gearboxes attached to them. This is a gearbox, and this is the encoder which gives the feedback. Then, because it is a smaller robot, and so to keep the center of gravity low, all the motors are installed here. In larger robots, the motors will be present at individual joints also, because the robot itself is so bulky that the weight of the motor is very small as compared to the overall weight of the robot. Now in this case, because the robot is not bulky, it has a payload capacity of 500 gram only. So the motors have been installed at a location so that the center of gravity of the robot is it makes it stable. Now the motors then, through the gear and pulley arrangements, right? So they drive the individual joints. So as I said, they are DC servo motors. They have a gear attached to them as well as an encoder attached to them. Encoders we will discuss when we go to the sensor part. So let us first of all see what is a servo motor. A servo motor is a motor which has a feedback mechanism attached to it. So here we see is an exploded view of an AC servo motor. So this diagram is for an AC servo motor. So this is the casing, and then this is the rotor, and then this is the stator. So this is the shaft where the load will be attached, but at the back of the motor, an encoder is attached. So this is the encoder which will provide the feedback. Now, this is a slightly, you can say, a line diagram indicating how the things work. So if we have a motor, whether AC or DC, so this is the back side of the shaft. So through the gear assembly, a potentiometer is attached to this, and the output of the potentiometer is given to a controller, and to the controller we also give a reference input signal, and then depending upon these two signals, the controller will either stop or start the motor, or it may be we may be even changing the speed also of the motor. Now if because DC motors and stepper motors, they form they are very popular motors on the robots. So if we discuss the basic working of a DC motor, so here what we have is we have a stator, which is a permanent magnet. For small motor, it can be electromagnet for large motors. Now in the magnetic field created by the stator, there is a coil, and that coil is attached to a battery source. Now in this position, you see that the battery is positive is this. So the conventional current will flow like this through the coil and then come back here. Now when the conventional current flows through this, so there is a basic principle in physics that whenever a current carrying conductor is placed in a magnetic field, it will experience a force. That is basically, that force is equal to I into L cross B, or ILB sine theta, where theta is the angle between the magnetic field and the direction of the conductor. Now here let us see that how does this force act. So here we are seeing a magnetic field indicated by these red lines, and this is a current carrying conductor, and by using Fleming's left hand rule, so where this middle finger, it represents the direction of the magnetic field. So here also it is from north to south, right? So the finger will point in this direction. This represents the direction of the current. So if you look at this diagram, in this leg of the coil, the current is flowing from the upper side to the lower side, or you can say it is flowing towards you. So then the force will act in the upward direction, so given by the thumb. So here this one will have a force which is acting in the upward direction, and since the current flowing in this leg is in the opposite direction, so this will experience a force acting in the downward direction, and therefore as indicated by this arrow, this blue arrow, the coil will rotate in the clockwise direction. But now when the coil rotates, because there are wires attached to it, so wires will get coiled up. So there has to be some mechanism where the wires don't get coiled up, number one. Number two, always the force acts in the same direction. That is possible if the current is always flowing on the left side of the coil in this direction and on the right side of the coil in this direction. For that purpose, we have commutators and brushes in DC motors. So these wires from the power source, they are not, you can say, connected to the to the system through some fixed joints, but they slide against the commutator through these brushes. So when this rotates, the commutator will also rotate, and the commutator or the split ring, it is in two halves. When it rotates, ultimately this orange part will come in contact with this side and the yellow part will come in contact with this side. So with that, our purpose of having the current flowing in the coil in the same direction will be served, and the motor will experience a torque in the same direction. Now, the DC motors, because of the commutator and brushes, so they are a little bit less efficient because there's a friction which is experienced. So we also have brushless permanent magnet motors. So there the BLDC motors are called brushless DC motors. They have rotor as a permanent magnet and stator as field coils. Now the role is reverse. There, this rotor is a permanent magnet, and here we have the field coils. So what is the principle? That the current carrying conductor in a magnetic field experiences a force. The principle remains the same. Now what will happen? The field coils, they will experience a force because a current is passed through them and they are a magnetic field of the rotor. Now the stator coils are fixed. They cannot move. So, and there'll be a Newton's third law of motion. Now the rotor, which is a magnet, that experiences an equal and opposite force, and because it is free to rotate, it is mounted in bearings, so it will start to rotate. Now here also we need to switch the current in the field coil so that the rotor keeps on rotating in the same direction, and that's done electronically. Typically, what are called as Hall effect sensors are used in BLDC motors. We will discuss this in our next part of this. So the Hall effect sensors are used to electronically switch the current in the stator fields. The features of BLDC motors are that they have high performance, high reliability because there are no friction is not there, low maintenance, quieter operation, and higher speed. So the main thing is that this commutator and brushes part is removed. We can fix the wires from the power source to the field coils. Then we come to the stepper motors. Stepper motors are open loop motors. Right? So when we say servo motors, they give us the feedback. And by virtue of that feedback, we are able to rotate the motor through desired angle. For example, if I want to move the one joint of the robot through say 30 degree, then I need to rotate the motor for that joint through 30 degree. So once start the motor, the encoder attached to the motor will give us the feedback, and once come to know that the motor has rotated through 30 degree, we will stop the motor. That's a closed loop. But in stepper motor, it is the open loop. So how open loop is achieved? This is achieved by making the stepper motor run through a certain steps. So for example, if it is running through each step size of 2 degree, so for giving it a rotation of 30 degree, I need to rotate it to move it through 15 steps. So that 15 into 2, we get 30 degree. So how it is made to rotate in steps? By giving it a signal in terms of pulses. So the pulses are given and the motor will move in steps. So by knowing the step size of a motor and by knowing what is the total angle through which we want to move the motor, we will give the motor that many pulses of the signal. So some usual step sizes are given here, 1.8 to 2.55, so on, so large. Now, there are micro stepping circuitries available where the stepper motors can rotate through very, very fine steps. For example, written here, 10,000 steps per revolution. That means 360 degree by 10,000. So that much resolution is there. So such a fine resolution is required where very fine operations are needed. For example, the motors of the hard disk drives of the computers, they are typically having a micro stepping circuitry because there the motor has to be moved very precisely. Then similarly, the say some robots which are used in surgery, in medical surgery, they will have very highly motors with fine steps. It can be a stepper or it can be even servo motors, but there are very, very having a very good resolution. Each motor costing maybe 2 lakhs, 3 lakh rupees. Now, stepper motors are primarily of two types, permanent magnet type and variable reluctance type, and the third is the hybrid type. So before we proceed further, let us see a small video. Here you will see the motor moving through steps. So this is the motor which will move through steps, and this is a you can say the controller of the motor made in a lab because it's a breadboard. The otherwise the controllers are or the driver circuits are on a PCB, printed circuit boards, but this is in a laboratory, in a college laboratory or a university laboratory. So this is a breadboard, this is a microcontroller. So you will see the motor moving in steps.
Here we have a stepper motor from a hard drive from a computer that's being driven by a PIC microcontroller. It's running a PIC Basic Pro program that generates a square wave that sequences the coils in the stepper through a set of transistors in the step rate of the motor. Right now it's stepping at a very slow speed, and you can notice the classic second order system response where you get overshoot and oscillation on each step. This system has very little damping. Now that the speed is increasing, we're starting to get closer and closer to the natural frequency of this motor system. When we reach the natural frequency, you're going to get resonance, so the amplitude will grow so large that the electronics will try to force the motor to do something that it can't, and it will miss some steps. And we're getting close to that right now. Very large amplitude oscillation. There are the missteps. As the speed increases further, eventually the motor will sync up again with the magnetic fields, and the rotation rate will again correspond with the square wave output from the chip. There it is, we're back in sync now. When the speed of the square wave from the chip is increased quickly, the motor has a lot of momentum now. So as the magnetic fields are stepped around the perimeter, the rotor keeps up with those, and the result is a very smooth motion.
Okay, so what you just saw in this video is that this is a microcontroller, and there's a program in the microcontroller which is producing square pulses, a signal of square pulses. And this signal is given to this part of the circuit where there are some transistors and resistances are there. So for each pulse, the motor rotates through one small step. That is its basic step size. Then during the video, you also saw that the motor almost became unstable during one period. So that was the period when uh, its natural frequency coincided with the frequency of the pulses. And after that, it became again stable and it started to rotate almost continuously, because then the frequency of the pulses became too high. So here is a, let us say if there's a 1 second period. So maybe we are giving 4 pulses. But if during the same period, if we give more number of pulses, then naturally the speed of the motor will increase. So because for each pulse received, it will move through one step angle. So this is a microcontroller, and we will see in the next slides that there are driver circuits. Here the driver circuit has been made in a laboratory, but otherwise the driver circuits are in the form of PCBs. So before that, let us see the basic stepper motor construction. So what you see on this screen is that there is a stator, then there is a rotor, and on the stator we have stator poles, and on the rotor we have rotor poles. Now here on the stator poles, there are coils wound, and if you see here, there are 6 stator poles in this diagram: 1, 2, 3, 4, 5, 6. And also pay attention to the alphabets written on there. So this is A, this is A minus, this is B, this is B minus, this is C, this is C minus. So there are 6 stator poles and 3 phases. And you see that the rotor poles are 4 in number: 1, 2, 3, 4. So rotor poles here are shown to be less in number as compared to stator poles. So this diagram is basically of a variable reluctance type stepper motor. So this is a basic nomenclature. Let us see, go to the next slide. So these are the stepper motors which I have taken a shot. There in our laboratory, the students use them for projects. So this slide I'm showing you to give you a basic specifications. Like the motor on the left hand side, it has a torque of 5 kg centimeter. It requires a current of 0.6 ampere, and its step angle is 1.8 degree. Similarly, motor on the right hand side, it gives us a larger torque, and so because it's giving us a more torque, so it requires more current, and its step angle is also 1.8 degree. So all these number of wires, they will go to the motor driver circuit, which will then drive this, because they are going to for the different phases. So I have not written here that you can see on the Google that how many phases it has and how many poles it has. Now, what is the basic principle of operation of a permanent magnet stepper motor? So here we see there is a this is a stator, and inside there is a rotor which is a permanent magnet. So this stator has 4 poles: 1, 2, 3, 4, and 2 phases. Phase 1 is indicated by orange color and phase 2 is indicated by the blue color. Right now, the phase 1 is energized and there is no power given to phase 2. As you can see in this diagram, phase 1 is high and phase 2 is low. Because phase 1 is high, so these poles of the stator, they are magnetized. So this is north and this is south. So naturally, this permanent magnet wherever it may be, but once they are and the stator poles are energized, it will align with the stator poles. North pole with the south and south pole of the rotor with the north of the stator. Now, if we want to rotate it further through one step, what we have to do is, because this is north, we will this one as south and this one as north. Right. So now what we'll do is, the next step, we will make the first phase as 0. That is, we will demagnetize these two stator poles and we will magnetize these two stator poles. The effect will be this. The rotor will move through 90 degree. Then in the third, now we give the reverse polarity to the first phase and we make the second phase as 0 again. So as a result, it will move further. In the first step, this was south, this was north. Now we are making this as south, this is north. So it will keep on moving further like this. So you keep on changing the two phases and the magnet will keep rotating through 90 degree. So to have smaller step, you need to have a larger number of poles in a permanent stepper motor. Then we have a variable reluctance stepper motor step sequence. So what is that? So in a variable reluctance stepper motor, as you can see here, we are showing, I think 8 poles. Yeah, there are 8 poles of the stator and 6 poles on the rotor. So this first phase is making this as south and this as north. Okay. Now in the rotor poles, there is one pole on which a black dot has been made. So this black dot is necessary to understand the operation of this motor. So this is aligned like this. So why it is aligned like this? Now this is not a permanent magnet. It is simply a steel rotor. So why it is aligned like this? Because you know that like a magnetic field, we have been performing, say, laboratory experiments in our school days, that if you have you sprinkle some iron fillings on a sheet of paper and then you keep once you bring a magnet on that paper, the iron fillings will arrange themselves in a certain pattern. So why? Because the magnetic lines of force, when they flow, although they are imaginary lines, but they will like to follow the path of least resistance. So when we talk of electricity and when we talk of DC currents, we use the word resistance, that is opposition to flow. But when we talk of AC currents, then we use the word impedance. That's again basically opposition to the flow. And when we are talking of magnetic fields, then the word we use is reluctance. That is opposition to the flow. So, and the opposite of reluctance is permeability. So whatever that is able. So a path which offers less reluctance, that is suitable to the magnetic field. So what the magnetic field will do is, it will try to, once this one pole has been made south and the other has been made north, so whatever is the position of the rotor, the magnetic field will pull the rotor in such a way that the gap between the rotor poles and the stator poles here, it becomes smallest possible. Now let us see the next step. Now say we make the second pole as we magnetize the second pole, right? Okay. Earlier this was south, now we make this as south. Once we make this as south, this rotor will tend to move in such a way that there is a minimum possible space between the rotor and the stator poles. Now you can see this pole of the rotor, it is away from this stator pole as compared to this one. This is nearer. So what the magnetic field will do is, it will rotate the rotor in the anti-clockwise direction, so that these two poles, this pole and this pole, they become aligned with the magnetic stator poles. So it will move in a anti-clockwise direction. So again, then we make the next activate the next phase. Then we activate the next phase. So there are 4 phases. So just keep on activating these 4 phases and the motor will keep on rotating. So here for the 4 steps, this plot shows that what is the status of the phase. For the first step, the first phase is high, all the 3 are low. Then the second phase is high, all 3 are low. So there is a major difference that here changing the direction is little bit difficult, because in the case of a permanent magnetic stepper motor, by changing the polarity of the magnetic field, you can change the direction of rotation. Here it is not that it's not possible. So hybrid stepper motors are used where you can have very small step angles and where you can change the direction of the rotation easily. So they are both the effects of permanent magnet and the variable reluctance they are used. So what you see on the screen is a driver circuit for the stepper motors that you saw earlier. They are available in our lab. So this green is the driver circuit. So we have a program in the microcontroller which will give a signal to the stepper motor driver, and the stepper motor driver will then drive the stepper motor. Right? So this is the microcontroller. So this ribbon cable that you see, it is used to burn the program in the microcontroller. Then from the microcontroller, this ribbon cable, it carries the signal to the stepper motor driver circuit. And then accordingly, from the stepper motor driver circuit, here you can see the current is provided to the motors in steps so that they are able to move. So thereby changing the power supply to different poles. So apart from DC motors and stepper motors, another very important actuators in motors and robots are fluid power actuators. They can be pneumatic, they can be hydraulic. We use pneumatic actuators where the power requirement is not very high, but some quick actions are required. And we use hydraulic actuators where the power requirements are very high and the motion can be slow also. So in this, we will just through this diagram and there's an animation also, we will understand the basic working of a fluid power actuator. So this is for basically for a pneumatic circuit, but for a hydraulic circuit, the difference is not much. So here we see that there is a cylinder, pneumatic cylinder, which is double acting. By double acting, we mean that you push it forward and you bring it back, both by the control of compressed air. Now, what is this? This is a directional control valve whose purpose is to control the direction of air. Right? And this valve, if it contains 5 ports, 1, 2, 3, 4, 5. So these 2 ports are called working ports, A and B. One port is connected to one side of the piston and the other port is connected to the other side of the piston. Now this central port is the pressure port, which is connected to the power supply. So this symbol is for what is called as an FRL unit in pneumatic circuits, filtration, regulation and lubrication unit. And then there are 2 more ports which are exhaust ports. So in case of a hydraulic circuit, we will have, instead of 5, we will have 4 ports, and the 4th port will be common for exhaust. There we don't call it exhaust, we call it return, because there the oil has to be returned to the sump. So here we are using air, so air we just release to the atmosphere, because we are also taking air from the atmosphere into the compressor for compressing and then giving it to the circuit. Now inside this there is a spool. So a spool, this has, you can see it's basically a rod on which there are three portions which have a larger diameter. And there's a spring on this side. And here what we have is a coil, basically. We call it solenoid. Now, in this position where you see, if we give a compressed air supply, the supply will come inside and the compressed air will be forced through A into the inside of the on the left side of the piston. The B port is blocked from the pressure supply by this what is called as a land, this of the spool. So when that happens, the air will go on the left hand side of the piston. The pressure of the air multiplied by the area of the piston, that will result in a force acting on the piston, and the piston will move towards right hand side. Now if we want to bring it back, what we will do is we will say close this switch. The switch will provide a current to the circuit will provide a current to the coil in the solenoid, and when that coil is energized, it will pull the spool towards the left. The principle is same, that whenever a coil is energized, it will produce a magnetic field, and the magnetic field will try to have a path of least reluctance. So it will try to have a core which is, say, typically a ferrous core, so that the spool will move towards left, because there's a air here, and when this core moves to the left, the reluctance of the magnetic field decreases. So when it moves towards the left against this spring force, what will happen? These three portions will move towards left. So the pressure port will now be connected to the exhaust, the working port B, and this will be connected to the exhaust port R. Right. So then the air from this side will go out, and the compressed air will go on the right hand side, and the piston will move back. So we will now see this in animation. So the animation, the dark blue color indicates compressed air. So you see here, when the this is closed, it becomes red, indicating that it is being given power. So, and then when it is not given power, when the coil is de-energized, the spring will push the spool towards right. In some cases, you will have two coils instead of one coil, and a spring you will have two coils. So when one coil is energized, the spool moves in the second coil is energized, the spool moves in the other direction. Let us once more see the animation. So when the switch is pressed, now the piston will move backward. So on pressing the switch, you can see how does this spool move towards left, and on the releasing the switch, it moves towards right. So this was a say linear motor, you can say, hydraulic motor. So you also have seen the rotary motors, which are typically pneumatic. I think all of us must have seen, because if you go to get your say wheel changed to a mechanic, he will, instead of manually loosening or tightening the nuts on the wheel, the mechanics these days, they use what is called as nut runners. So they run with the pneumatic supply. Now a few more slides on this to indicate that in the animation that I showed you a switch. So this switch is being manually operated, but actually we are talking of automation, robotics. So there, here, if this kind of a switch is there, you will need a person or maybe something else to operate it. But actually what happens, that instead of the switch here, these switches are electronic switches, typical like transistor based switches. So they will operate this load. So how it happened? So I am showing here. So you can imagine that this is the solenoid of the directional control valve, and this is a manual switch. So if you close it, then only the current will flow. So this is the supply. VCC means the supply, and 0 means ground. So then only the current will flow. So rather than this switch, what we have is an electronic switch. So like here we are showing a simple transistor, an NPN transistor. So here you can see that the path to the transistor is reverse bias, so the current cannot flow from here. The current can flow through the collector and the emitter only when a signal is received on the base side. Once that signal is received, it becomes conducting, and then the current can flow. So it is equivalent to manually operating operating this kind of manual switch. So there is not much of a difference in the sense that here also you can see there are three terminals. One terminal, second terminal, and the third thing is the force required to operate this. So it can be a mechanical force. Whereas in this case, you have these two terminals, and now instead of the force, what you have is a electrical signal in terms of a voltage. So when that voltage signal is given, the transistor will become conducting and the current can flow, and whatever load is attached here, that load will work. It may be a bulb, it may be a solenoid, it may be a motor, anything. So with this overview of actuators, now we will come to sensors. So first of all, we will have a look at the sensors which are available on this particular robot. So as I said that servo motors, they have encoders at the end of their on one side of the shaft. So this is the motor on the our motors line diagram of the motors on our robot. So these two leads, they show that plus and minus for the motor. That is the current supply to the motor. Then here it shows four leads. One is ground, one it shows VLED, P1 and P0. So what is this we will see here. If you look at this exploded view, so if you open this, then it looks like this. Right? So what it has, encoder has is, encoder has, sorry. So this has basically, this is a shaft from the motor and there is a disc mounted on it. Right? So this disc has a number of holes in it. Right? And this disc rotates along with the shaft. It rotates between these two LEDs and these two transistors. And the disc will move through them like this. So let me change the color of the pen. So that is how the disc is rotating. So it has holes on the peripheries. Now this is an LED source and the other one LED source, right? And these two are the photodiodes. So the light from this LED can fall on this photodiode only when a hole becomes collinear with this LED and the photodiode. So when that happens, this photodiode, it will produce a pulse. Similarly, there's a second pair of LEDs and photodiodes. So they will also produce a pulse when a hole is in between them. So with the pulses that they produce, they will give us an indication of the rotation. We will understand the concept in the next slide. So let's first of all go through the slide, and the location and movement of each axis is measured by an electro-optical encoder attached to the shaft of the motor which drives the axis. So encoders can be optical, they can be magnetic, They can be some other type of things, but in this robot there are optical encoders are there. And also the number of holes on this pitch circle diameter, in case of our motors, there are 500 holes are there. So you can see 360 degree by 500 the position of these encoders. So when the robot axis moves, then there's a series of alternating high and low electrical signals. The number of signals is proportional to the amount of axis rotation, and the sequence of the signals indicates the direction of movement. So what does this mean? So here we consider the concept. So this is the LED. So the light from here will fall on this phototransistor when the hole is in line with them. So when that happens, we will have a pulse as the hole passes through this. It is rotating. So after this one has passed, when the next one comes, then one more pulse will be generated. Then the third one comes, and then the third pulse will be generated. Then the fourth one comes, then the fourth pulse will be generated. So you can see that by counting the number of pulses, we can come to know how much the motor has rotated. For example, if there are 2 pulses, for this example, we know the rotation is 90 degree. Also, the frequency of the pulses will tell us the speed of the motor. The number of pulses will tell us the angle through which the motor has rotated, and the frequency of the pulses will tell us the speed of the motor. Now, how to come to know the direction of the rotation? That is done by having 2 pairs, as we saw in our previous slide. That is on the first slide of the encoders, that there are, instead of 1 pair of LED and photodiode, we'll have 2 pairs of LEDs and photodiodes. So there will be a certain lag between the 2 pulses, and in the you can say in the signal conditioning and in the associated circuitry, it is seen by having seeing the lag between these two. The direction of the rotation is also determined. So the next sensor that we have on our robot is the cam and micro switch. So you can see for each joint there is a cam and a micro switch pair. Cam and a micro switch pair here. So this is the photograph of that. So this cam is a very small profile. So if this is the cam, it is almost a circular disc, but at one point there's a very small profile. So this is actually visible here, but may not be. It may not be. You may not be able to make it out, but there is a very small profile here, which will press this switch. Right. So when the switch is pressed, a circuit is completed. So this is a micro switch, is basically a spring-loaded switch, or an ordinary spring-loaded switch. So what is the use of the use of this is that this, with the help of these, robot marks its reference position. So let me show you a video where the robot is doing homing. Homing is that when we start the robot, it will take all its joints to its 0 position. So this is the same robot which you saw in that performing an operation. Now we will show you its homing position. So what you will see is that it moving its joints one by one, slowly, repeatedly. Okay. And then I think you will also be able to see the computer screen lying on that side. There the homing is going on, and once the homing is complete, you will see a dialog box on the screen will automatically close. moving its elbow joint. Moving its gripper, what we call a roll. This is the roll. This is the pitch. This motion is called the pitch of the tool or the wrist. And here you can see a dialog box for moving. Now it is moving its shoulder joint slowly. Now elbow, again elbow joint. It will move each joint in two directions, and it will see that when this cam, it presses the switch, it will take that position as the home position. So this dialog box that you see on the screen, it will automatically close when the homing is complete. Now it is the second shoulder joint, it is moving. Now testing the gripper. And now you see the dialog box closes, so homing is complete. So when it moves these joints, it moves them in both the directions, and at the point where this cam, it presses this micro switch, the robot then takes that position of each joint as the home position. Okay. So this is the micro switch of the Scorbot robot. So it has 5 micro switches, one on each axis, which serve to identify the robot's home position. During the homing procedure, the robot joints are moved one at a time. Each axis is moved until its home switch is activated. The axis is then moved slightly until the switch shuts off. At that point, the joint is at home. When all the joints are at home, the robot is at home, which is the point of reference for robot operations. So as you can see, it has 2 terminals and a switch. So if you connect something between these 2 terminals, when the switch is pressed, that thing may work or that thing may not work depending upon the type of switch we are having. So what we are showing here is a generic limit switch or a micro switch. Now it has 3 terminals, and instead of a simple button which is spring loaded from inside, it has a small lever which is spring loaded from inside, and this lever here basically has a roller over here, right? So that if there is, say, on a lathe machine, a tool post is moving. So when that tool post will come from this side, it will roll over this roller and this lever will be pressed. And so then a signal is given. So let us see a little bit of detail of micro switches. This is the inside of a micro switch. You see 3 terminals. You can say 1, 2, and 3. Right. Now let us say we attach something between 1 and 2. So we put a simple battery, and we put a simple bulb between 1 and 2. So this is a simple bulb. Right? So you will see these are metallic contacts. Obviously current can flow through them, but here at this point there is an air gap. So this bulb will not work. But when you press this lever down, this air gap will close, this air gap will close and the circuit will be, this circuit will be complete. Now let us say we have another circuit between 1 and 3. So now the circuit between 1 and 3 is through this from here. So what you see here is here the circuit is by default complete. So when the switch is not pressed, the circuit is complete and this bulb will glow. But when you press this switch, these contacts, they will make here contact and these two contacts will open. So then this will be off. So basically 1 and 2, the 1 and 2 contacts they make is called as normally open contacts, and 1 and 3 contacts they make what is called as normally closed contacts. Normally means when the switch is not operated. So when the switch is not operated, 1 and 2 are open, but 1 and 3 are closed at that time. And when the switch is closed, 1 and 2 are opened and 1 and 3 are 1 and 2 are closed and 1 and 3 are open. So if you want something to work when the switch is pressed, then you connect it between 1 and 2. And if you want something to work when the switch is not pressed, then you connect it between 1 and 3. Okay. Now, so on our robot, the sensors installed are these two, the encoders and the micro switches. But let us see some more sensors which are typically used in robots and how they can be used actually. So for that, let's have a very brief introduction to the controller. So this is the back side of our controller. So where you see there's a D50 connector. So it has a 50 pins. So all the robot motors, the encoders on the robot motors, the micro switches, they all connect to the controller through this D50 connector. Then this is the cable for the teach pendant. It is a RJ45 connector like your telephone jack. Then this is the USB cable which connects the controller to the computer on which the program is installed. Now this is the front side of the robot. Now if we again recollect our first video that we saw where the robot was performing a pick and place operation. So it was going to a predetermined location, picking up a wooden block and taking it to the second place. Now if I had not placed a wooden block there, the robot would still have performed the same operation. It would have gone to that point, open the gripper, it will close the gripper, move up, go to second position. So the robot was doing something, but we can add a little bit of intelligence to it by say putting a proximity switch at the place where the object is to be there. And that proximity switch or proximity sensor, we will then, how we will give its output to the controller, we will by connecting that proximity sensor to the controller through these. So these are the portions which we can make use of. So in that case, in the program, we will add a if statement that if the sensor is giving a signal, then only the robot will open the gripper and grasp the object. Otherwise, the robot will simply wait. So similarly, there can be other things also that we cannot have a proximity sensor, or maybe we can have another proximity sensor for collision detection, so that there may be something else near the object. So in this case, something else is there, so we don't want the robot to move. So we can stop the robot somewhat away. Or if maybe instead of a now a proximity switch will be a yes no type. That, for example, I said that if the object is there, the robot will perform the operation. If the component is not there, the robot will not perform the operation. But let us see another, it's a yes no type. Let us see another situation. Say the payload of my robot is 500 gram. So I want that the robot should pick the object only if its weight is less than equal to 500 gram. If the weight is more, I don't want the robot to perform the operation. So I may have a small load cell under the surface on which the robot is to, the component is to be placed. Now, if the load cell will give us a reading of the weight of the component. So if that reading is say up to 500, I can say, okay, go ahead. If it is more than 500, I don't want to do it, right? So that, or there can still be another more complex scenario, right? For example, when the object is gripping, when the robot gripper is gripping an object, so we can have pressure sensors to come to know that what type of object it is. It is a hard or it is a soft, and accordingly we can manipulate the force that the gripper is applying on the object. So in these scenarios, we may be giving a analog signal to the controller, right? That is, which can vary in value. For example, temperature. Temperature in the room, it's an analog signal. It can go from maybe 5 degree or 6 degree in winter to maybe 40 degree in summer. So it's a variable. It's not a yes no kind of thing. So we can have there, here we have available input and output ports for connecting external sensors and actuators. Maybe I don't know whether it's clearly, but there is inputs, outputs, and there are digital inputs, and there are analog inputs and outputs there, and there are two more ports available for connecting additional motors. So they have D9 connection. So let us first of all see the proximity sensors, because we also have a couple of videos recorded in our laboratory to give you an idea of say binary or analog type of sensors. So when I say proximity sensors, so we can have capacitive type, inductive type, infrared type, optical type, variety of sensors. So what you see here is a capacitive sensor, but an inductive sensor will also look exactly like same physically. Typically, a sensor will have three terminals. Two terminals are used to give it a power supply, like here we have attached a 9-volt battery here. Then the output of the sensor is detected on the third terminal. Now this is a capacitive proximity sensor. This has a range of about 8 millimeter. So if an object is up to 8 millimeter away, it can detect that object. So how does it detect? If the object is absent, the voltage across this terminal and the ground, it is 0. If the object is present, the voltage is same as that is supplied to it. So let us first of all see its video. Friends, you see here a capacitive proximity sensor, a 9-volt cell attached to the sensor, and the output of the sensor attached to the multimeter. Right now you see a 0-volt reading on the multimeter. When I will bring my finger near the proximity sensor, this LED on the sensor will glow and the reading on the multimeter will change. Watch. Now you see the reading on the multimeter is almost 9 volt and the LED is glowing. As I take my finger away from the sensor, the reading becomes 0 and the LED also goes off. So the output on the multimeter is the voltage output from the sensor. So when the output of the sensor is attached to a controller, for example, a programmable logic controller, the PLC will come to know about the presence of the object when the voltage is detected at the input port of the PLC, like now. Right? The LED is a visual indicator for the human operator. So 0 volt, full volt. So it is a binary sensor, yes, no type of sensor. So as it is a capacitive sensor, it can detect either an insulator or a conductor like a metal. Thank you very much. Okay, so when now these two terminals, this black and this blue wire, what we will do is we will connect them here, right? So these are the digital inputs. So we will connect the black and blue in this line. This is for the inputs. So that is how we can make the robot become aware of the environment. Now, very briefly, how does a capacitive sensor work? A capacitive sensor can detect conductors as well as insulators. So as the name suggests, it works on the principle of capacitance. So that is when you give a power supply to it, the sensor will act as one plate of the capacitor and the target will act as another plate of the capacitor. So an electrostatic field is set up by the sensor. Whenever the target comes near it, the capacitance increases and there is an oscillator circuit in the sensor which begins to give higher oscillations. So when the higher oscillations are detected, then that means the target is present. At that time, this trigger is typically what is called as a Schmidt trigger system. It will give an output of the sensor. And when the target is absent, the oscillations are very low. And when the target is present, the oscillations are high. But a Schmidt trigger will give the signal when the oscillations are high. A similar look sensor is an inductive proximity sensor. In an inductive proximity sensor, what we have is that we have a coil and there is an oscillator which will generate a alternating signal through this coil, thereby producing a electromagnetic field. So when nothing is present, the magnetic field has its own strength. However, whenever a metallic object comes near it, the magnetic field will induce eddy currents in the target, and due to that its energy is reduced and the oscillations they become reduced. So when the oscillations they fall below a certain limit, then the Schmidt trigger will give a signal. So in case of a inductive proximity sensor, when the oscillations are there when the target is absent, and oscillations are absent when the target is there. So when you have to distinguish between conducting and non-conducting objects, then you will use inductive proximity sensors. Otherwise, you can use capacitive proximity sensors. And also you can use infrared light IR sensors or optical sensors, which are also called obstacle sensors. So IR sensors, okay, we'll have it. So that also we'll discuss in the next slides. So here we are showing you a screenshot of an inductive sensor pickup in our laboratory. So this is the inductive proximity sensor, and these are the connections. Now there is a disc. The disc has a teeth on it, and two teeth here are missing. So when the disc is rotating, there's actually a motor mounted on the other side of this plate, which is rotating this shaft. So whenever one tooth passes in front of the inductive proximity sensor, a single pulse will be produced. So I will show you the screenshot from our computer. So here you see the train of pulses. And whenever this portion passes where the teeth are missing, there is a gap here. So when 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pulses and the gap is present, we come to know it is all 360 degree. So, and the frequency of pulses will give us the speed of the motor. of the shaft. Then IR sensors, they are typically like this, that there's an infrared LED which will give out infrared radiation which are not visible to our eye. So when the object is not there, the IR radiation will simply scatter. But when the object is there, they will be reflected back on a photosensitive diode or a photodiode. And when that happens, some circuit will be complete and a output will be detected on this side. Next, we have potentiometers. So these capacitive proximity sensors, inductive, IR. So they are all binary type of sensor, yes, no type. Now here we are looking at a potentiometer, which is a very simplest possible analog sensor, which converts a mechanical signal into a voltage signal. All our radio knobs, our fan regulators, they are all basically potentiometers. So what we have here is this is a symbol at a very simple so a potentiometer is essentially a resistance. So what we have is, say we attach a 9-volt battery here. So if this is this, the conventional current will flow like this. Now, if I admire, so let's call, let me just, because let me make this as plus, this as minus, because I want to explain in the next slide. Okay. So we have done a current flowing like this, right? I. So it is positive terminal, we normally call it 1, and the ground as 3, and this as the 2. This as 2. So the current is flowing through this resistance, and let us say this resistance value is R, capital R. Now if we try to measure a voltage when the slider contact 2 is here, this output voltage will be current through the resistor multiplied the value of the resistance. Now here the value of the resistance is this, which is less than capital R. So the voltage, output voltage will be less than this input voltage that we are giving. But if the slider is over here, then the output voltage will be same as the input voltage. And if the slider is here, the output voltage will be practically 0. So let us see a video of this also. For this analog potentiometer.
Friends, we see here a linear potentiometer attached to a 9-volt battery. The output terminals of the linear potentiometer are attached to the terminals of the multimeter. Right now you see a 0-volt reading on the multimeter. Now potentiometer is a analog device. It converts displacement signal into voltage signal. So as I will move slider, the voltage on the multimeter will change continuously from 0 to a maximum voltage which is supplied by the cell. So this device, it transduces a displacement signal, which is a mechanical signal, into voltage signal, which is electrical signal. So this sensor is a analog sensor as compared to the capacitive proximity sensor, which we had seen earlier, which is a binary sensor. Thank you.
Okay. So this is a rotary potentiometer, so which is same as the linear one, but here you see it is the rotary motion is detected and converted into a analog signal, an electrical signal. Then in robots, we typically have range finders which are based on ultrasonic principle. So very basic principle that the sensor will emit a quick burst of a ultrasound, 50 kilohertz. You know, human range is 20 hertz to 20 kilohertz. And then the outgoing sound will be reflected back by the object and detected by the receiving signal. So it measures the elapsed time until the receiver indicates that an echo is detected. And very simple rule, distance is equal to velocity in time. So distance is the round trip distance going and coming back. V is the speed of propagation because the speed of the ultrasonics is same as sound, 340 meter per second. And so it's that is the how much time has been elapsed. So in the nature, bats, dolphins, they make use of ultrasonic signals to detect the objects. Then Hall effect sensor. As I told you that in BLDC motors, Hall effect sensors are used. They are very, very reliable sensors because they are also non-contact type. So the basic principle of Hall effect is, let's say this is a plate which is connected to a DC supply. So obviously the current is flowing like this. Now because the potential difference is across the length of the plate, so if we try to measure a potential difference across the width of the plate, there will be a zero reading. But what happens if a magnet is brought near it? Due to the magnetic field which interacts with the electrostatic field here, the electrons will shift to one side. So one side will become negative, the other side will become positive. So therefore, a voltage will be detected, which is called as Hall voltage. Now, nearer the magnet is, higher will be the Hall voltage. So this sensor is used. It can be used as a proximity sensor. It can be used as to measure the distance also. It's a very, very useful sensor. Then in robots, we have inertial sensors like typically gyroscopes and accelerometers. Gyroscopes are typically used to measure the rotation and accelerometers to measure the acceleration. So there are applications are, of course, heading sensors. Nowadays, even our phones have gyroscopes and accelerometers. So otherwise, when we talk of gyroscope, the picture that comes to our mind is that there are three gimbals and then there is a disc in it. They are mechanical ones, but this gyroscopes, they have a very small structure. So there they have two sensing arms and one, two sensing arm, no, sorry, two which call it driver arm and one sensing arm. So this is the stator, and even this you can take as two sensor arms because this is one and this is second. So normally when it is by the way of some say piezoelectric effect, it is given a vibration. So these two, they are given the vibration, but they will vibrate in this direction only, right? However, whenever the object will rotate, like your phone or the robot will rotate, what will happen? The sensing arms, so here it is shown, they will begin to vibrate like this also, and because of this vibration, these sensing arms, they will change their position. Rather than being straight, they will become little bit bent. And then this bending of the sensing arm is converted into an electrical signal. Again, you can use anything. You can use some resistance principle, capacitance principle, some piezoelectric principle to convert the motion of this sensing arm into a voltage signal. This is basically typically a digital gyroscope shown here. Similar is with the accelerometers. Accelerometers, so there the basic principle is that you have a mass, and when mass is accelerated, inertial force is created. So due to that force, either the strain gauges, they will deform, or we can have a piezoelectric material, and due to which here we can have an output voltage, but in case of strain gauges, we will typically have the Wheatstone bridge circuit from where we will get the output. But there it is shown a commercially available accelerometer. So whether it's a commercially available accelerometer or a gyroscope, their size is quite small, less than 1 inch by 1 inch by 1 inch. So, and also it includes all the electronic circuitry to produce the desired output signal. Similarly, we have temperature sensors. They can be of say 3 types: RTDs, NTC, thermocouples. Thermistors are the most widely used temperature sensors. So this is a resistance temperature detector, which is basically, it can be a copper, nickel or platinum wire, and when the temperature changes, the resistance will change. Same case in thermistors, but thermistors are semiconductors, they are metal oxide. So here it is written NTC. NTC means negative temperature coefficient. Like in nickel, copper, etc., when the temperature rises, the resistance rises. But in case of NTC thermistors, with increase in temperature, the resistance will fall. So here we show here that as temperature increases, RTD's output will increase because their resistance will increase. So depending upon your circuit, you can have it. And here for thermistors, the resistance will fall down, and we can have some output signal which will change. And these are thermocouples. It's a commercially available, very cheap temperature sensor shown, DHT11. And it's a dual sensor. It can measure temperature as well as moisture. So it uses a thermistor for temperature measurement and a capacitive element to measure the moisture. You see the dielectric basically changes due to moisture, and so the output changes. So it has 4 pins. This is the VCC supply, this is the ground, and this is the data. So you will get the output between data and the ground. So this fourth is shown NC. NC means here NC is not connected. It is not used because sometimes the manufacturers, they keep an extra pin for future uses. So based on the same principles, strain gauges, capacitor, piezoelectric can have pressure sensors. And this is a commercially available around 400-500 rupees pressure sensor called force sensitive resistor. So it has 3 layers. This is the conducting one, and this is a spacer, and this is the third layer. So these are the active portions. So as the more pressure is applied, the active dots, more and more active dots, they come in contact with this semiconductor material, and as a result of which the resistance of the sensor will go down. So these days on assembly lines, RFID tags are quite frequently used. Even we also use RFID tags, like our you see these tags, fast tags, which we use on toll plaza. So they are also RFID tags. So RFID tags are radio frequency identification tags. So what you have is like your fast tag which you have on your car or any other vehicle. So it has a tag a small chip which contains the information about your vehicle, and there is an antenna outside. So when the reader, it gives out a radio frequency signal, that radio frequency signal will induce a current in the antenna, and the chip in which the information is there, that chip powers up. And when it powers up, it relays the information back to the reader, right? So in this way, so here it is shown, this is the antenna on the tag, and this is the chip which actually contains all the information. and here on the finger it is shown that how small the chip is. So RFID tags can be two types. They can be passive and active. Passive are which are, say, as I said, on typically in our fast tags. But active RFID tags will have a voltage, have a battery with them, so they will intermittently keep on giving out a signal. So typically, sometimes active RFID tags are attached on components and assembly line so that its position can be tracked. So they have different frequency ranges. Higher frequency range means that they can detect it to a higher distance, a larger distance. So friends, with that I come to the end of my presentation. So if there are any queries you can ask. If there are any questions you can ask.
Yes, thank you so much, sir. It was
Madam.
very, very interesting session. So yes, dear all, please ask your queries if you have any, and you can also post your queries in chat box. Yes, let me check. Sir, one query we have is how do we calibrate sensors?
Well, you see, you calibrate sensors by giving it a known input and then measuring the output. Like, say, for example, if I have to, on academic level, I'm saying if we have to say, if a student is given a spring and told, okay, find what is stiffness, what is spring constant. So what he can do is he can attach known weights to it and measure the extension in the spring and then plot those values, and then from there the plot he can find out that what is the slope between the weight applied and the extension, and so you can find k. So similarly in all sensors you give a known input to the sensor, measure the output, and from there you can by that you can calibrate it.
Okay, sir. Thank you. And next question we have is how do we decide which sensor is to be used, and how we decide which motor should be used?
You see, which first thing sensor to be used. So that depends upon the parameter you're going to measure. For example, if you're going to measure a temperature signal, then you have to use a temperature sensor. Now, which type of temperature sensor? That will depend upon number of factors. For example, what is the range of the temperature you want to measure? Then what is the resolution that you want to measure? That is, if you want to measure say 20 degree and 20.1 also, or it is 20 and 20.5 is okay. Then how fast you want the response of the sensor, because every system it will take some time to acquire a signal and to give the output. For example, if you are using in our homes, we use earlier we normally used mercury in glass thermometers. It required around say 80 seconds to give you the temperature reading. But nowadays we use digital thermometers, so which will give you the response in 1 second or 2 seconds. So the range, the resolution, the response time, these are the main factors that we, and of course the cost that we consider while choosing a sensor. And as far as choosing a motor is concerned, the first thing you need to know is that, okay, what is the power requirement? And in power also further, what is the ratio of your torque and your speed requirement? Accordingly, you will select a motor. Because if we come take a different type of motors, obviously AC motors are called workhorses. They are used for very high power requirement. And if you don't require a high power requirement, you will use a DC motor. But if you require a very precise speed control, then you may prefer a DC motor. So ultimately it comes out to that what is your power requirements, what is your torque requirement, and what is your speed requirement. So based upon that, you will select a motor.
Okay. Thank you, sir. Next question we have is there any online virtual lab available for learning these sensors?
You see, if you Google it, you may find it. There will be a number of sessions, but that's something very interesting thing if somebody can do it, because uh, virtually what you can do is maybe how do you operate a sensor? That is the thing, right? Of course, you see, there are like when we play games, we make use of say haptic sensors. For example, if you are driving a car, and if the car is on a rough road, the joystick that you are holding in your hand, so that joystick will give you a vibration in proportion to the say the roughness on the road in the game, like that. So if we can feel such a thing, that is good. But otherwise, by a virtual app can only be that you can see something working on the screen, or maybe there is something that you give an input and it gives you an output. But there are some virtual labs. There, in fact, NPTEL has some virtual labs, not particularly about sensors. There may be about sensors also. I have seen some labs uh, which relate to some other things. Even I don't remember now which ones I have seen, but there are some virtual labs available.
Okay, sir. Thank you. Sir, next question we have from Mr. Kulbir Singh. Can sensors be used to feel the smell?
Of course, you see, since that there are, I think I already read that there are some chemical sensors available which you can attach to your PC. So, for example, I'm saying that you are watching a movie on the screen, and if a particular scene comes up like that, so that chemical sensor will release a smell which will be according to the scene that you are watching on the movie.
Okay, sir. Yes, thank you so much, sir. You explained it in very graceful manner. It was very, very interesting. Thank you so much for your kind presence.
Thank you,
Thank
ma'am.
you so much.
Thank you all the participants. Thank you one and all.
Dear participant, next session will be resumed at 11:30. Till time you have a virtual tea break, and we will meet at sharp 11:30. Attendance link is already posted in WhatsApp group and here chat books also. Kindly make sure you have to mark each and attendance of every session. Thanks all. No, separate link will be shared with all of you with WhatsApp books, and on in a PDF already it was shared on your email.